So I'll say that again. Today we're going to finish up talking about linked lists. Okay. We'll also talk a little bit about the test. So tomorrow is going to be both a lab and a review day. Okay. So I'll start off doing a little review. Then we'll have a lab assignment that we can work on. Okay. And then on Monday, we'll have the exam. The exam, you have to be on Zoom. You have to have your camera on like you normally do for an online exam. Okay. And I'm not looking for this to be a gigantically long and difficult exam, but we'll talk more about that tomorrow. But we'll be programming only, no other kinds of questions. It will be open book, open note, open internet, open whatever you want.
Wait, you said it was which Monday? This coming Monday or the next one?
This coming Monday.
Okay.
Okay. Okay, so on the linked list, we talked yesterday about what a linked list does. We had story time with all the different things that we can do. There's one more bit of storytelling we need to do, and that's we're going to implement this as an abstract data type, something we can't directly create an instance of. The reason being there are two basic types of linked lists that we can do, and the book talks about that in the way it's defining things. Okay. The first is if the order of the linked list is random, just a unordered list. Okay, there's no order to it. You can put in whatever you want, wherever you want. Okay. The other thing you can do, of course, is that you can maintain the list to be in order the whole time. Okay, so we have ordered lists and unordered lists. So for a lot of those, it's going to be exactly the same. There's not going to be any difference. Okay. And to be able to be as efficient as possible, the book made the reasonable decision to create this linked list.h, which is, or linked list type, I think they call it .h, which has an implementation of a linked list that has some virtual functions for things that are different. Okay, so it turns out what's different about unordered lists and ordered lists. Okay, first off, when you're inserting a new item, into a linked list, an unordered linked list, it doesn't really matter. Okay, and the way they define the linked list, remember our list itself, the list node, each individual node only contains one bit of information and a link to the next one. But the linked list object is going to contain as its member data a link to the first node, okay, a link to the last node, and then a count of how many nodes that there are, okay, that we can use for other purposes. Okay, so we're going to bundle all that up. We could add more to that. We could have less if we wanted, but that's the basic idea. Okay, so since we have the first and we have the last, then we have the ability on an unordered list to insert a new node either at the beginning or at the end. So the add node has some different issues there. Okay. We also have differences when we're searching. If you're searching an ordered list, then once the current info is greater than the term you're searching for, you're done. You're not going to find any further down the list. On an unordered list, you have to go the whole way. Okay, you can't stop early. Okay, the deletion could be a little bit different in how we're going to have to rearrange things. Printing should be the same, and all that. Okay, so when the author of the book put together the linked list.h, which you should type in, I think I said that yesterday. The homework problems I think work best unless you want to just implement your own from scratch, which isn't really the nature of the homework problem. You want to start with those examples. Okay, so again, the linked list type, I believe it is, .h. Okay, as part of that, it creates this linked list iterator. And the iterator is just going to work like the iterators we did with the standard template library. Okay, it's going to define the only member data it has. I'm on page 281 if you have the book with you. It defines as its member data a current pointer to a node type. Okay, and then it's going to have a constructor. It's going to have a dereferencing operator. It's going to have an addition, an increment and decrement operator. And it's going to redefine the equality and not equality, so equal and not equal. Okay, going to redefine those functions. The book's provided that for you. You can copy and paste it. Again, if you have time, I think there's an advantage in typing that yourself. So let's go ahead and take a look at what that looks like. Okay, I've got all that stuff over in my directory here. So let's take a look at that. Share the screen here. Okay. So yeah, it's the linked list.h, I believe is what they call. Yeah, so again, it starts with a struct of the node type, which is going to contain just info and then a link. Okay. And again, this is templated. So we're going to do the class type here. It's whatever type of info you want. You want to make it of doubles, ants, whatever. Okay. Again, it's certainly possible to add more bits of info here if you need it. Okay. We'll talk about some other types that do that. But in general, that's what we have. We have one bit of data called info. We have a link to the next thing. Okay. And then here is the iterator class. Okay. So it starts off here with the function prototypes, and they do a good job of explaining what they do here. So we have our default constructor. Okay, that when, and again, it gives a post condition, which is a useful thing to have in functions. So what should be the case after you run this? It should be that you have the current, which is the only thing that the class iterator is going to maintain, should point to null. You've created a new empty one. Okay. You can also take a parameter of an existing pointer to a node that you can then set that to current. And that's what the second one does. Okay. And then we have here going to overload the dereferencing operator, okay, to be able to point to info, not to the node. It doesn't have a lot of meaning to dereference a pointer to a node because a node has more than one thing, but it's the info that we care about. Okay. We're also going to overload the pre-increment operator. Okay. So with this, the iterator is advanced to the next node. In this case, there's not a decrement. We're only going to go forward. Okay. We're going to overload the equality operator, the two equal signs here. Okay. With that,
overloading.
Yes.
Overloading the pre-increment, does that automatically overload the post-increment as well, or is it?
It doesn't. You would have to use the operator, the plus plus before, not after. So plus plus variable instead of variable plus plus.
I mean, like the overload here rather than not the. I'm a bit confused how you would write that as like operator.
Okay, so what you would do, it's a unary operator. So if you had a linked list called L, you could say L plus plus. No, you would say plus plus L because it's the pre.
But does this exclusively do the pre-increment? Like if you wrote, say L plus plus wouldn't work. You'd have to write plus plus L.
I think that's correct, but I don't think I've, except in this example, I don't think I've ever overwritten that operator before. We could do that to C, but the pre-increment is the one that happens on the left. I don't know how you would make it on the right. I don't know if that even makes any sense. So I'm not sure what that point is there that they're doing, but I mean, the point is you can't, what the increment does is in a normal sense would just move to the next memory block over, but these are not continuous or contiguous. Okay, so we have to follow the link basically. So we're gonna have to make sure that that plus plus follows the link of the current node, okay, which is the purpose. And we'll see how they implement it in a minute to see which way that works out. Okay, that's kind of thing for me. I would try it one way. If it doesn't work, I'd try it the other, and surely one of them should work. Okay. And then with the iterator or with the operators equal signs, okay, again, we're still in the iterator. It's going to return true if the iterator is equal to the other, otherwise it's false. There's also a not equal there. Okay. And then the only data we're keeping here is a pointer to a current node type. Okay. So that's all that has. Okay. So all of that is the iterator. Okay, then we're going to go through and actually implement those things. Okay, so again, with our default constructor, we just have that the current's equal to null, and that's it. Okay, then with the other type of constructor, it's going to take a node type of type, which is confusing, pointer, and then it's going to set current to that. Okay. And then again, on the dereferencing operator, we're going to return in particular current.info, not current itself. Okay, because we're storing a memory address. So this would return a memory address if we didn't overload that operator. Okay. And then on the plus plus, again, all that's doing is moving it forward. So it's setting current to be current link. It's going to go one more down the line on the iterator. Okay. And it returns a this. Okay. And it does that because it has to return an actual iterator object. Okay. The this returns to current. Okay. It's the record that you're sending back. Okay. Let's see what this one is. The equal operator on this one, it's going to return if current, looking at the right current, that's what's on the other side of the equal sign. The same thing with the not equal. Okay. And we would have to have that or wouldn't work out normally. Okay. So after that's defined, we're next going to go to this abstract class for the linked list type. Again, abstract class just means that there are virtual functions, pure virtual functions, which means we can't instantiate it directly. Okay. In this case, we're going to create an obligation in the children of this class. So having all this typed in does not give you the ability to make a linked list. We're going to have another class that derives from this that fills in the blanks, basically. Okay. But on this one, again, I usually go to the bottom to start with. What are we keeping track of? Okay, so in this case, we go down to the private, or protected in this case. There's private too, okay, but the protected is where the data is at, okay? We have an int for the count. That's going to be how many elements are on the list. That's going to give us the ability to have a length function that we can do. And then we have two pointers to node of type, whatever type they are, to the first and to the last node, just to keep track of those. You don't have to have those, but it gives us some flexibility, especially if we go with things like the circular list where the end comes back around at the beginning, other things like that. Okay. And there is one function here, the copy list. So it's going to be a deep copy function, okay, in essence. So now let's look at the actual functions that we're going to be defining. Again, some of these we're actually defining. Some of them we're doing as pure virtual functions, okay. So we start with, again, we have memory data here, so we have to reassign the assignment operator, okay? So we have to overload that operator, okay, the equal operator, okay? So we're gonna do that first. We're gonna have the function here to initialize the list, which will just make it go to an empty state. So if there's stuff there, it's going to wipe it all out, okay, and make sure that both first and last pointers both point to null and that the count is 0, okay. We have a Boolean function to see if the list is empty or not. It's going to be true if it's empty and false if not, okay. We have a print function, which is going to use the iterator to go through node by node from first to last, and it's going to print out the info at each of those nodes along the way, okay. There's a length function that simply returns the length of the list. How many nodes are there? Again, all of these so far, all these are not virtual. You don't have to read it. We're going to redefine them under this, and then we don't have to redefine them for whether it's an unordered or an ordered list. It's going to be the same.
I have a question real
Yes.
quick, Fraser.
Yes.
Okay, so you know how you have all, like, just all of these under one file, pretty much like a
Yes.
.h file?
Yes.
So we can do the same, right? Like we can put all of those under wow. Wow, that makes it so much easier. Like, because my problem when I was doing it was I was having a hard time figuring out where some stopped.
Yes.
And then where some wanted me to start again.
Well,
like for different files. So I was just like kind of confused.
Well, and then you have to include them all, and it gets confusing. Yeah, you can do it all as one. Yeah, it's not a problem.
Okay, that makes it easier. Thank you.
Yeah, it does. You lose some flexibility potentially, but it's not a problem. Okay.
Yeah.
Okay, so again, all of these are the same for ordered or unordered. It's not going to matter. Okay. Same with the story list. It's going to delete all the nodes from the list And again, take that back to first, last, point and all, and the count being 0. There's a function front, which is going to return the first element of the list. Okay, and for this, the list can't be empty. And if the list is empty, then the program's going to terminate. Otherwise, the first element of the list is going to be returned. Okay, so again, not a pointer to that node, but the actual value of that first. Okay, because it returns the type. Same thing with back. It's going to be that last element. Okay. And then we now have a virtual function. Okay, so it's the first one. And this is a pure virtual. We know that because we've got this equal 0 over here. Okay. Virtual just means that it can be redefined in the children class. A pure virtual means that it has to be redefined. Okay. And won't be defined here at all. Okay, but this equals 0, which is a weird way to do it, but that's what they chose. It won't be defined in this file, but you'll have to derive another class from it for either unordered or unordered. Okay. Same thing with this insert first. Okay, the insert first only makes sense if it's an unordered list. Ordered list is going to have a different issue. Okay. So we also have an insert last, another pure virtual function. Delete node. Okay, it's going to be different depending on whether it's ordered or unordered. Okay. We then have a function of that's going to return the linked list iterator for begin. So it's the beginning of the list. Same thing for end. Okay, so those return the iterators that we can then do those functions on. Okay, that's not going to vary based on whether or not it's ordered or unordered. Okay, same with the default constructor. Same with the copy constructor, same with the destructor, which is going to delete all the nodes. Okay. And this divide mid is one of the homework problems. So we won't look too much at that, except that's where you would put that. Okay. If you want to divide it into 2 sublists, this is where you would put that declaration. You got to put it here and then make sure it gets implemented properly. Okay. So we've got, yeah, that stuff. So then we go through and just define these. Okay, so if it's empty, then we're going to return if the first is equal to null. Again, we need this function because first is not private, it's not public, so we can't get to it directly. So we need this function to do that. We have our default constructor. If it's a brand new list, the first is equal to null, the last is equal to null, the count equal to 0. Okay. We have the destroy list. Okay, where we're going to create a temp node type. Okay, we're going to set going through, and again, we don't have all of those. We're going to have to iterate through as long as there's something there and set temp to the current node. We're going to advance first then. So temp captures the old first node. We're making first go to the second node. And we don't know where that's at in advance until we do this. Then we can delete temp. So we've deleted that first node. We're going to inch through and do that. Okay. And then finally the last we set to null. And we're going to set the count to 0. And we should be done on that. Okay. The initialize list, all it really does is destroy list. We've already got that function. So we're going to go ahead and just tie that together. Okay. Print function again is going to use the current pointer to a node type of some type. It's going to set current equal to first and then do our while current not equal to null, the normal way we do things. It's going to print current info, a space, and then print or then advance by setting current equal to current link. Okay. The length function, again, we keep track of the count. The count's just the length, but that's private data, so we have to write a function to access that to return the current count. Okay. We then have the first function here, or sorry, the front. What the front does, and I think we've talked about assert, but if we haven't, the assert, I think we had to include something for assert. Assert just looks for a logical condition to be true. If it's true, it ignores it and goes on. If not, it's going to stop the program with an insertion error. So in this case, we're going to assert that first is not null. If it's not null, then we're going to return the info of that. Okay. Because the issue, if you don't test for that, then you're going to get some random junk in there, if not a segmentation fault. Okay. Same thing here with the back. Okay, it's going to take the last .info there. Okay. And then these are the ones that return the iterators. The begin is just going to create a temp that points to first, and then it's going to return that temp. Okay, it's going to create a linked list iterator with that temp first. Okay, and then it's going to remember that was one of the constructors to take another pointer and tie it to that. Okay. And then we have the end works a similar way. We have the copy list here, which is going to take and go through one by one. It's going to destroy the list on non-empty. If it's not empty, it's going to make it empty. It's going to go through bit by bit and set those values. Okay, and that's what we're doing here. Where current is equal to other first, all the way down. Copy all the nodes. Okay. Again, this is all in the book, and it's all laid out there. Okay. The destructor is just going to call the destroy list, get rid of everything, clear the memory one by one. We saw that before. Okay, so this is going to be the copy constructor. If we send it another list, that's going to copy that list using the copy list. Okay, which we already did. Here we're overloading the assignment operator, so it doesn't do just a memory address to memory address copy, but actually does a list by list. Again, it's going to use a copy list. We've already defined that. Okay. Divide mid, we don't talk about. I think that may be all that's there. That's how that one more. That's the homework. Yeah, that's it. Okay. So that's what the link list .h. Again, it's a .h, but it has both the prototypes. It's got the struct for the node. It's got the prototypes for the linked list iterator and the definitions for those. And it's got the function prototypes for the linked list type and all the definitions of those, all in one header file. Makes it easy. Okay. But again, we can't use that yet. Okay, so we're going to have to inherit that, or whatever the other way. We have to make a child of this, okay, or a subclass of this that implements either an ordered or an unordered list. Okay, and this is from the book too. So let's go ahead and look at what this looks like. Okay. So again, we're putting our protection here, the if, not if, and define. Okay. We're going to do that in case it doesn't try to include it twice, which could be a problem. Okay. So again, this is straight from the book. We're going to include the linked list.h. So we have all of that stuff, all that abstract class data for the iterator and for the linked list type. They're all there. Okay. We're then going to create this new class, unordered linked list, and it's going to inherit in a public fashion from the linked list type with some type. Okay. So all the stuff that's in the linked list type, we now have available in the unordered linked list. Okay. We're now going to have to put some functions in here that we have an obligation to do. We had the obligation to do a search. It takes a search term and does a search and searches through it, looks through the list. So we have to redefine that one. Okay. Again, the constants are there because we don't want changes to be made. We're going to insert first. Okay, so the constant here, there are two constants, just so we're clear. This constant refers to the fact that the search term itself that we're sending in is not going to be changed. Okay, where this constant means that the list itself is not going to change. So the search shouldn't change anything. It should just return a number or return a Boolean, true or false. It doesn't return a position. Okay, the insert first is going to change the list. So there's no constant over here, but there is a constant here, and that the item that we're adding shouldn't change outside of this program. Okay. Same thing with insert last. Again, we're not going to have these on an ordered list, but unordered list we can insert first and last. Why there and nowhere else? Well, we don't really know anything else, right? We know the first, we know the last. We have pointers to those two nodes. We know how many nodes there are. We still don't know how. We don't know how to get there, right? We have to go to the first and follow through. It's the only way to get there. Okay. So those are the things we have to do. Also the delete. The delete's different as well. So we didn't do print, for example. We didn't do a constructor, okay? We didn't because an unordered list is a list. An unordered linked list is a linked list. So we can use that constructor. We can use that print function. We can use the destroy and the copy list, all that stuff we were using before. So all we're defining here, what we have to define here is those pure virtual functions that have to have a definition, okay? So we then go through, look at these, for example, on the search here for the unordered linked list. We're going to send it a search term. Okay, we're going to again have our current. We have a Boolean whether it's found or not, and then we're going to set the current to the first one, and we're just going to keep going through. Okay, so we're going to, as long as two things now, we've got as long as the current isn't equal to null, which means we're done. We're done with items, and we haven't found it yet. Okay, so if found is true, then that's all going to kick out. Also going to kick out. Then we're just looking to see if the current info is equal to what we're looking for. If so, then the found becomes true, and it'll kick us out the next time around. Else, we're going to move on to the next one. So at every move, we found it and we're done, or we've moved down the line and we've either got one more to search or we're hit a null and we're at the end. And then it's going to return found. So found was set by default to be false. If it became true, then true gets returned. If it never becomes true, gets to the end instead, it returns false. Okay. So here's the insert first. So again, it's going to take a new item to insert into the list. Okay, so in this case, it's unordered. We don't care about the relative positions of the other elements. Okay, so all we're going to do here is we're going to take the first. Okay, so we're going to start by creating a new node, new pointer to a new node type called new node. Okay, we're then going to actually create that new node and allocate the memory with the new command. So this new node pointers are going to be equal to new node type of whatever type it is. Okay, we're sending type in again as a parameter. So we're then going to set the new node info to whatever item we're sending in. We want to add a node that has an int of 7. Well, then we're going to set that the new node, which isn't, it only pointed to by new node. It doesn't connect into our linked list yet. And then we're going to set the new node. We went through this in story time yesterday. The new node link is going to go to that first one because this is becoming the new first. Okay. We then can set first equal to new node. To do those in the right order, we've lost the rest of the list. Okay. And since we're adding a new one here, then we're going to set the count up 1. Okay. And yeah, that will increment the count by 1. Okay. And then we're checking here if last is currently equal to null, which meant we started with an empty list and we've inserted it the first. Well, now the first is the last, and that's all we're checking for there. Okay. The other thing we can do then, we can insert a last. Okay, insert at the end. Does that go too far? Probably, yeah. Okay, so on that one, again, we're going to send an item for it. Okay, so with that one, we're going to create, again, a new node, a pointer to a new node, and then we're going to allocate the memory for it so it has a spot in memory. Okay, we're then going to set the info, and the link here is going to be null because this is going to be the new last item. The last item has its link go to null. Okay, and then we're going to check here to make sure that the first is not null. If first is null, then we just have one element. So first is both the new node and the last node, and the last node, first and last, and we're done. Okay. Else it's not, then we have to change the link of last to point to this new node we've added at the end, and then the last becomes that new node. And again, we're going to increase the count in either case, either of the if else's, because in both cases we're adding another element to the list. Okay. We don't care about repeats. We don't care about order. It's unordered. We put whatever. It could be a list of 21s, and that'd be okay. Okay. We then have the delete node here. So again, with this one, it's going to have, we've mentioned this before, they're calling it current and trail current, but that's the same as I think we said previous and current. So the current is going to be a pointer to the node that we're on as we go through, that we're checking to see if it's the one to delete. the trail current pointer is the one before that. So they're going to move in tandem. Okay. And again, we're going to have a found here, just in case, if you try to delete 12 and there's no 12, you need to know that. Okay. So we're first checking to see if the list is empty. Okay. There is an is empty list function that you could use, but for whatever reason here, they're just checking to see if first is null, there is no list. Okay. So you can't delete from an empty list. Okay. But if that's not true, then we're going to go through and we're starting at this first item. And if we're at the first item, so they're listing the cases here. So when you go to delete, the case is that the list is empty. That's fine. It could be the case that we have found the current item, okay, right away, the very first one, okay. So if that's the case, then we're going to set current equal to first equal to first link. Okay, so we're deleting the first item. This is a delete from head. We're just moving. We had 1, 2. We're going to skip and go straight. The first is now the second one. Okay, and then we're going to decrement the count. Okay, and then we have to check to see, since we're keeping track of the last, if the list now only has one node, then first and last are both equal to the same thing. Okay, and then we're going to delete the current pointer that we set up. Okay. The if here is if this is this inner if here, if it's not the first info. Okay. Then we're going to have to search the list to find the correct node. Okay. So in this case, we're going to set found equal to false, and we're going to set the trail current equal to first. We've already just checked first, so we're not having to check first again. Okay. And then we're setting the current equal to first link, so to the next one. So the very first time this hits, trail current set to the first node and current set to the second node. Okay. We're then going to go through and as long as, like our search before, as long as we're not at the end, so the current's not equal to null, and as long as the found hasn't become true, then we're going to keep looking to see if we found the current item to delete. Okay. If we have, okay, then we're going to say found is equal to true. Okay. We're not doing anything else yet. We're just finding. Okay. We're not deleting. But we're going to keep going through. And if the current info is not what we're looking for to delete, we're going to increment. The trail current is going to go to current, and current's going to go to current link. You could also say trail current goes to trail current link, and it would do the same thing, but they're doing it this way. Okay. So again, if we were at the first time, we were pointing to the first with trail current and the second with current, we would now be pointing to trail current would now point to the second also, and current points now to the third, and you start again. Okay. Once it becomes found, so you've hit this while here because this is false, so it is equal to that. So this will kick out, and then you'll come down here and you can do this if found. Okay. So if it's not found, of course, so we've made it all the way through to the end, and this terminal condition hits rather than this one, then the found will still be false. And we'll just have to say that the item to be deleted is not found in the list. Okay. But if it is found, okay, so think of where it's found. It's found where current points to the node that contains the info we want to delete. Trail current points to the one before that. Okay. So let's say we're at trail current points to 5, current points to 6. Okay. Current link will point to node 7. So we want to point node 5 to node 7. Okay. So point 5, the pointer to 5 is the trail current link. We want that link from 5, the trail current link, to go to not current, which it currently does, but current link, which is 7. Okay. And again, we're going to decrease the count. Again, we then have to check to see if the node was the last node. So if last is now equal to the current, then we're going to set the last equal to the trail current and delete current from the list. Okay. So that's the delete. All we have to do there. Okay. And that's it. We've defined everything else that we need to define. Okay. So now if you were going to use this unordered list type in a program, you would include it. You don't need to include the linked list.h because this includes the linked list.h. Okay, so you include this unordered linked list dot h, and then you can start using all the functions not only of this unordered link, but the other as well. Okay, so the book goes into a lot of detail on that as well, defining all that stuff. Let's see what else we got there. It goes in a little more detail than I did on all the things that we're doing, all the function. There's the unordered list that it puts together. Okay. Then it gives the header file. Then the next thing it talks about, which I don't have a copy of, but it's a similar idea that we're going to have the ordered linked list. Okay, so the ordered linked list, again, on page 300, is going to go through and have a search, an insert, insert first, insert last, delete node. And that's all it's going to have. Okay. And the book also, starting on page 300, goes through and defines or describes what all those look like and how those work. Then it gives the file for that as well. Okay. And then finally on page 309, it's going to give us a program that tests the various operations on an ordered linked list. Okay, so again, we just include the ordered linked list, and then we're going to be able to create an ordered linked list from the constructor and go through and run through the functions. Okay, so that example will be helpful to make sure that you've got that down correctly. Okay, are there questions on the abstract data type or the unordered or ordered lists? Again, there's examples in the book on how to use it. Okay, so far so good. So there are a couple of other things for us to talk about in this chapter, other things we can do with links or lists. The first is on page 310 on the doubly linked list. Okay, and this is the idea that you can go not only forwards but backwards. Okay, so you're going to add to the node, to the struct itself, not only a link. You're going to replace link. You're still going to have an info, but you're going to have a previous and a next. Okay, so all the things we could do before, going forward, you can't, but now you can also go backwards. Okay, so this adds functionality to the linked list, but it also adds weight, right? It adds more computational complexity. We have more to deal with. But if that's something that you need, then that's something that you need. Okay. So in the book on page 311, it goes through and does a class specification to do the basic properties of an ordered double linked list. Okay, so all of that gets put together on the class doubly linked list. It's not going to pull from linked list because it's got a different structure, but it has its own functions there. Okay, it's then going to go through and define all of those functions that it tells about. Okay, so that the book doesn't put it in the format of a .h file with everything. It gives you the .h file, and then you could define each of those in the same program if you want, but they're separated by text, but it explains how that works. Okay, and again, as you would imagine, both inserting a new node and deleting a node get a little more complicated in that you have both of those pointers to keep track of. Okay, and it really is important that when you're trying to visualize these and looking for the issues you're going to have, that you have to make some pictures. Okay, so let's pop up the whiteboard on the iPad again and take a look at how to think about these things and how we could draw them. Okay, so with a doubly linked list, I tend to draw them this way. Okay, so if you have a series of these, you saw the data, whatever's there. And again, it could be ordered or unordered. Okay. So the initial previous is going to be a null, but next points to the next node. Okay. This has a previous node that points back there and a next node that points there. This has a previous node that points there and a next node that's a null. Okay. So you can imagine if you're going to delete this guy, you would have to route a couple of things. Okay. You would have to make sure that this node now points to there, and also that this previous node points back to there. Okay. So there's just a little more to deal with. Okay. And the same way, if you're going to insert a node, okay, there's more to track. So again, with our inserting nodes, let's say we want something between 7 and 10. We start in the code by creating a new node with whatever info we're adding there. Okay. And again, we have to worry about the case. Is it the beginning? Is it the end? Is it the middle? If it's in the middle, then we would have to make sure that we're going to route the previous back to that one. Okay. We have to route the next back to that one. Okay. But we also have to reroute this next to here and this previous to here. Okay. And again, you have to make sure that you don't cut off the branch that you're standing on. Okay. And if in doubt, you can always add a temp to store things. It's often not a bad idea when you're dealing with these, just to create a temp pointer when you're not sure. So if you happen to lose it, you're still going to have a way to recover that. Okay. You don't always need to do that, but that's the basic idea there. Okay. The book at the end of this chapter talks about the standard template library sequence container called list. And there's some things you can do with a list. There's different ways it can do things. There's an example there. I'm not overly concerned with that right now. I think that it's good to look at, but we're not gonna worry too much about that. Okay. So the other parts of this chapter, there's a section linked list with a header and trailer nodes. Okay, with that, it's going to be a linked list, especially if it's an ordered linked list. If you're inserting or deleting at the beginning or the end. So you can create a node here called a header at the beginning of the list that's going to have a value smaller than the smallest value. And then you can have a trailer at the end having one that's bigger than the others. And that's just going to be a way, those header and trailer nodes are just a way to kind of keep track of everything that you can use sometimes. Again, we're not going to do much with that. Then we also have the idea of a circular list. And a circular list, I mean, it's fairly straightforward. It can be either a double circular, but usually it's a regular circular. And with that, again, if you have a normal linked list, look like this. You have 3 nodes, okay, 3, 14, 2. Okay, but in this case, that points to there, that points to there, this one points back to there. Okay, and that's the only idea. Sometimes it's useful if you have a series of values you're going to go through and go back to the beginning every time, then you can implement it that way. And that requires some other changes. Okay. Another good example there, if you're still confused about this stuff, on the video store, again, if you have the PDF, you can copy and paste that, but I encourage you when you can to type in stuff yourself, function by function. I think you'll have a better understanding as to what's going on. Okay. So that gets us to the end of the chapter. We can talk a little bit about the homework problems that we have, okay, and how we could go about doing those. Okay, so the first one is program 4, dividing a list into 2 sublists of almost equal sizes. Okay, so that's going to be a function we're going to add, and it gives us here what its description is going to be as far as a prototype. We have a void function called divide mid, which takes as its parameter a linked list type of some type. We're going to call that sublist. Okay, so it's going to divide the given list into 2 sublists of almost equal size. So the first points to the first node and last points to the last node of the first sublist. You have a sublist up first, that points to the first node, and sublist.last points to the last node of the second sublist. Okay. So it's going to give us some things we can do there, some examples that we can do, what it's going to look like. Okay. And it wants you to write the definition of the function to implement that operation, and then write a program to test that. Okay. So for that, when you would put it into the linked list type, I think you can make the assumption, I mean, it seems to me, I'm reasoning it on the fly here, that it's not going to matter whether or not that you use a ordered or unordered list. It's going to be the same thing. Okay. But in your example program, you have to pick one of those. You have to pick unordered, it's the easier one. So you're going to have, before you do this homework problem, you have to have typed or copied from the book and working the linked list.h and the unordered linked list.h. Okay. You're then going to have to modify the linked list where you can put it, where you're going to implement this divide mid function. The prototype will be up in the prototype section, and I showed you that when I was going through that file, and then you'll add at the bottom the actual function definition. Okay. But then when you go to write a test program, you're going to have to actually include the unordered or ordered, whichever one you have working. Okay. And then from that, you'll be able to test the function from there. Okay. So that assumes that that's already been done. Okay. There's also number 6. We're going to add another operation to the class ordered linked list for merge lists. And it again gives you what the prototype is going to look like. You put that into the ordered linked list. Again, we're just ordered in this case. So you now have to have the ordered working as well. Okay, so that code has to be there. There may be a place online to download that directly. I'm not really sure. I looked, and everything that I tried to download seemed to want me to have Windows, which I thought was weird. I think this is the one that did that. Yeah. So if you have Windows, maybe you can download the files. There should be a student version, but if not, you can cut and paste from the PDF. Okay. But you're also going to add a function to that class ordered linked list. And again, it tells you how that's supposed to work. Okay. And then also there's another program to test the various operations of the class doubly linked list. Okay. So again, copy or type in the doubly linked list function or header file. Once you have that, then write a program that imports that, creates 1 or 2, and then runs through all the functions. Okay, just to make sure we understand how to use these. Okay. So for right now, for our work today until 2, I want you, if you haven't already, to go ahead and get started on that first homework problem. Okay, so that means you have to make sure that you have the linked list.h working correctly, okay, and that you have the unordered linked list.h working correctly as well. Okay, we'll go ahead and write a test program. You can use a test program from the book that tests that, make sure that's functioning. Then you can go back and start working on this divide mid operation, where you're going to add to the linked list type. Okay, and we'll work on that for now. When we come back at 2 o'clock, you can ask any questions you have about that, or if you've already done that one, go ahead and continue to work on the other homework problems. We'll go from there. Okay, any questions about any of that stuff? Okay, well, we'll break for now then, and we'll come back at 2 o'clock, and I'll answer any questions that you have then. Okay, see you at 2.